This is a common data question where the common data in the circuit diagram is given. We have two sub questions for it. Let's see the question. In the circuit shown below, assume that the voltage drop across a forward bias diode is 0.7 volts, which means it is indicated that the cut-in voltage is 0.7 volts. The thermal voltage Vt equal to Kt by Q is 25 millivolts. The small signal input Vi is equal to Vp cos omega t, where Vp is given 100 millivolts. Now the first question is the bias current IDC through the diodes is. Now if you look at the circuit, there is a DC source here and an AC source here. As they are indicating, it's a small signal. We know from the small signal analysis part that we can do DC analysis and AC analysis separately. But of course, the AC analysis parameters depend on the bias values. So first question is based on DC biasing. So let's get to that. When we're doing DC analysis, we don't consider the AC sources. So we have 12.7 volt source and a 9900 ohm resistor here. And now as the diodes are indicated that they have a cut-in voltage of 0.7, we can substitute the diodes with an ideal diode in series with the cut-in voltage. But of course, as we know that there are only 4 diodes and the voltage applied is 12.7 volts, which would be enough to forward bias all the 4 diodes, as the cut-in voltage is just 0.7. When this ideal diode is forward biased, we will take it as short circuit. So we'll substitute for each diode with a voltage source like this. So hence we have 0.7 for each, indicating the cut-in voltage. In total, it is 2.8 volts. Now we are supposed to find the IDC. The IDC current that would be flowing here will be equal to 12.7 volts minus 2.8 volts divided by 9900 ohms, which is equal to 9.9 volts divided by 9900 ohms, which is equal to 1 milliamperes. So hence the correct answer is option A. In fact, we have done DC analysis here. Now let's move on to the AC analysis. When we go to AC analysis, we take all the DC sources to be 0. Hence, we're going to short the 12.7 volt supply and take only the circuit with AC supply, which is Vi. Of course, the resistor will be there, that is 9900 ohms. And now, for the diode, we have a small signal equivalent model, that is the diode resistance RD in parallel with diode capacitance. But of course, here capacitance values are not given, hence we are not taking the capacitance. We take RD. We know, of course, RD is equal to eta Vt over ID. When eta value is not given, we take it to be ideal, which will be 1 times Vt is given 25 millivolts divided by ID is 1 milliamperes we have found, where ID is the DC bias current. As we indicated at the start of the video that when we do AC analysis, the AC parameters would depend on DC biasing. Now this is equal to 25 ohms, which means each diode has 25 ohms resistance. So when we have 4 of them in series, we get 4 times 25 ohms, which is 100 ohms. Now we need to find what is the output voltage VAC. Now the voltage across 100 ohm resistor can be written as VAC is equal to 100 divided by 9900 plus 100. It's a voltage divider network times Vi. This is equal to 100 divided by 9900 plus 100 is 10,000. 100 over 10,000 is 1 over 100 times Vi is Vp, which is 100 millivolts times cos omega t. So this will be equal to 1 cos omega t millivolts. So this will be the output AC. So the correct option for the question 2 is option B, which is 1 cos omega t millivolts.